Good afternoon. I'm Jaron Rothkop, CTO of Zerobase Energy. I'm going to talk today about hybridizing 3 kilowatt generators. Next slide, please. So on the left is a system that the U.S. Marine Corps deployed as part of XFOB in 2010. And on the right is the tactical hybrid generator that we have on display just behind this room. These systems have roughly the same effect on the fuel consumption of a 3 kilowatt generator. The one on the left weighs around 2,500 pounds, and the one on the right weighs about 308 pounds. So we've made enormous gains in the last 5 years. Next slide. And that's our industry as a general. And that's the industry that's working on the expeditionary power challenges. We've reduced weight by over 7 times. We've had a 5-time improvement in cycle life. We've had fuel savings of similar hybrid systems of 2x, and the products are now compatible with both the new AMPS generators and legacy generators. And that's the industry working together. That's battery suppliers, solar module suppliers, power conversion devices, and companies like Zerobase. So I'm going to talk about the tactical hybrid generator, but I'm also going to talk a little bit about the path that we took to get to the product that we have on display today. So a little bit about Zerobase. Our focus is on expeditionary energy. We do power systems that are for austere environments that focus on fuel savings and ruggedization. We're mostly working around CA4ISR and power for shelters and contingency basing. And we're doing this in support of the Department of Defense's various missions, E2S2 inside of the Army, the Rapid Equipping Force and their customers, the U.S. Marine Corps, and the Office of the Secretary of Defense all have mandates and targets for reducing the overall consumption of fuels. And that gives companies like ours in industry targets to hit. But there are also markets in the commercial space that have similar needs. This is a vodka distillery in Maui that's running off of a microgrid that's using very much the same battery technology as our tactical hybrid generator. And then in the energy access world, which is mostly focused on aid and development, there's a different set of challenges that require some of the same technologies. In this case, is a project we did for USAID and EarthSpark International in Haiti that's focused more on effect and the ability to sustain these systems in very remote environments where the level of competency of the operators is going to be much less than those inside of the Department of Defense and U.S. Army. So our largest customer inside the Army has been the Rapid Equipping Force. We're part of the Energy to the Tactical Edge program, and their methodology benefited us a great deal. In identifying and understanding requirements, they showed us where the needs were that we could apply our technology to. In establishing partnerships, we understood what the path forward was. In selecting solutions, they introduced competition between the different vendors as to who had the best technologies and solutions. And then they equipped the units and assessed the impact, which gave us valuable data, which has informed the broader community of what the benefits of hybrid power are. And I don't need to show this audience pictures of burning fuel convoys or talk a bit about the benefits of renewable energy and its capabilities. I think others have done that before me. But there were some challenges in adopting these technologies. Customers were really unwilling to rely on solar alone initially. Hybridization was necessary because a lot of the operations weren't going to run off of just solar. There were advanced battery technologies, but a lot of the operators, and particularly the log folks, were concerned about their transport and their survivability in the field because there had been so many visible failures of lithium-ion batteries. Most of the equipment that was introduced to enable hybrid systems, particularly power conversion devices, were designed for first world environments or for vehicles and required a lot of hardening in order to survive in an expeditionary environment. There was really no baseline for operator training. The average soldier or Marine isn't familiar with the language of energy and how to manage their energy the way that they are familiar with how to operate generators. There are sustainment challenges, which the Rapid Equipping Force spoke a little bit about earlier today. The line that I heard repeatedly was, "There's no Home Depot in Afghanistan." something goes wrong, it's a long way from having a supply of COTS equipment. And from our end, the test protocols weren't especially designed. We understood generally how the equipment was going to be tested and qualified, but that changed depending on how it was being deployed, because the hybrid systems were neither a generator nor a battery system. However, the REF deployed quite a few of them successfully. This is one of our small hybrids running a mortar pit. This is a containerized weapon system running a 3 kilowatt generator with a small hybrid system and solar panels up on top of the container. So these were fairly small loads. Next up was a request from PMFSS to power a microgrid, a shelter system, where their requirements were at much higher levels. Aside from wanting to optimize the fuel consumption of the 15 kilowatt generator, which required three-phase output, the thrust of this program was to create a large power system that had a 4-man lift requirement. So it was the breaking down of the components into small modules, or in the case of the way we attacked the problem, using multiple versions of the forge system that we had and combining them together and having them communicate jointly to the shelter system controller with a high degree of autonomy. And so this is the system which is sitting up at NADEC powering the sustainable living module, and in the box you see the hybrid power components. The project was successful in showing that you could have a high-power mobile modular hybrid power system, but there was still one. Oh, sorry. Good. Keep going. I forgot to tell her to move the slides along. There we go. We've caught up. So this is the sustainable living module. We move on to the next one. And what the sustainable living module project didn't accomplish was eliminating the 15 kilowatt generator. So while the hybrid power system was man-portable, the generator was not. So the Rapid Equipping Force had a project that was looking at creating small mobile microgrids where all of the components would be man-portable. And the only man-portable generator that was available is the 3 kilowatt TQG. So the project objective was to take a number of these 3 kilowatt TQGs and network them together, and then be able to take any individual component and remove it from the system. Next slide. Some of the technologies we had were, we were starting with a AC source that was not able to be synchronized. And there have been some demonstrations of synchronizing the 3 kilowatt TQGs. However, those were fairly complex and fairly expensive. So our approach was to take the AC, convert it to DC, and then bring it into a three-phase 12 kilowatt pure sine wave inverter. We also needed a very high level of energy density in order to stay under the thresholds for man portability. So we're using lithium power batteries that were tested at the Marine Corps E2C that had a charge and discharge rate of over 2C, so they would be able to keep up with the 12 kilowatt requirement. Next slide, please. Sorry, next slide. Going. There we go. So this is a basic block diagram of the system, and it describes the components, but it doesn't describe how it would actually be fielded and what it would look like. Let's go to the next slide. So this is the system that's running the containerized weapon system. You can see the 3 kilowatt TQG off to the left, and you can see the components that make up the Forge hybrid power system. Now, a lot of the hybrid power systems that have been fielded look much like this. They're a collection of cases. There's reasons for this. There's a certain degree of modularity. There's a desire to keep the weight of individual components under a certain level. And also, they're designed to be very flexible. But we also were considering that in order to most effectively hybridize this TQG, we wanted to have a system that wouldn't have much additional weight and wouldn't have much of an additional footprint. So we had the advantage of approaching the problem with the goal of just focusing on the tactical quiet generator and its weight and its footprint. Next slide. Okay. So this is the result. On top you see the 3 kilowatt tactical quiet generator, and below you see what we call the 4 kilowatt tactical hybrid generator. The TQG bolts directly on top. The two units can be moved around together, or they can be separated so that they'll remain man-portable. Next slide. These are the results. The rated power goes from 3 kilowatts to 4 kilowatts, and the peak power goes from around 3.6 to 8 kilowatts because we're drawing on pure sine wave inverters attached to high-capacity batteries instead of being limited by the generator. Silent watch capacity, because of the battery, is 8 hours at a 1/3 load, which is typically what these generators are running, which means a second generator won't be necessary in order to perform maintenance on the first. The DC output almost doubles as we're coupling the systems by DC. The duty cycle is significantly reduced, and what that's going to do is affect the mean time between failures of the generator. And we're able to bring in solar directly into the unit, even though it was not fielded with it. It has the ability to bring in the secondary DC power directly to the DC bus. Next slide. So the flexibility of the system is it has the same footprint as a TQG. It has the same material handling. It can be lifted or forklifted in the same way. It has the same operator interfaces. So it uses the existing lugs and terminals and the same controls as the TQG. It can be retrofit to TQGs in the field, so the auto start kit that enables the generator to be turned on and off is a field retrofit. As mentioned, they can be separated, and the penalty for this is 308 pounds. Next slide. And the fuel saving numbers are going to be fairly dramatic. Compared to a 3 kilowatt TQG, the hybrid battery cycle alone will save 40% of the fuel. But because the THG and 3 kilowatt TQG combination can now handle peak power that's significantly higher, it can displace some of the amps that have been put into place just because of that high peak demand. And compared to an amps, you get 5 kilowatt amps, you get an even greater fuel reduction. So this translates into a fuel savings. It translates into a reduced number of fuel fill-ups, which means that the operators can be returned to the mission that they're on instead of running around with fuel cans, and a significant reduction in operating hours. And it's that reduction in operating hours that affects the mean time between failures of the generators, as well as allowing for long periods of silent watch, even when in normal cycling mode. So where does this fit? There's 26,000 3 kilowatt TQGs out in the field today, and they're not scheduled for replacement for some time. The THG isn't right for all of them, but where a 3 kilowatt TQG is running continuously and burning fuel, where the fuel supply lines are at risk, where the system is in mission critical application, or where the delivered price of fuel is very high, is a fit for this technology, which the Army now has under testing and is available today. Next slide. So thank you.